So till the last lectures we saw what was the importance of engine testing and performance. During all those times we talked about dynamometers. So what is the main function of dynamometers? It has two main functions. The first function is to load the engine, that is to apply certain load onto the engine. And the second function of the dynamometer is to measure the torque output of the engine. Okay, so these are the two main functions of dynamometers. In this lecture, we are going to see what are the different types of dynamometers that are generally used during the testing phase, right? So why is it important to know about dynamometers? The main reason is because there will be sums based on this. See, whenever you are going to do testing on an engine, I will just show you this diagram. See, for example, whenever you are going to do testing, in this case, see, in this case, we are not testing the engine. In this case, we are testing the output of a motor. Okay. So basically, what does the dynamometer do? A dynamometer is used to measure the output power of any rotational body. It can be a motor, it can be an engine. See, both motor and engine perform the same function. They give us what? They give us rotational power output. Motor does it through electric power and our engine does it through fuel power, right? They are both giving us rotational mechanical power, right? So how to measure the rotational mechanical power? Well, we use two things to measure the rotational mechanical power. What is the formula for rotational mechanical power? Power is equal to tau into 2 pi n upon 60, right? So out of this 2 pi and 60 is constant. We just need two things. One is the torque and one is the RPM. So this dynamometer is used to measure the torque. And if you look over here closely, this is a sensor which is basically being used to measure the RPM. So using these two things, we can measure the power output of this motor. Similar to this, rather than putting a motor over here, we can put an engine over here. And using this dynamometer and RPM setup, we can measure the power output of the engine. So that is what basically the function of dynamometer is. Dynamometer loads the engine and it is used to measure the torque output of the engine or any rotating body for that matter. Okay, so it measures only the torque output. It does not measure the RPM. For RPM, you need a different sensor. So that is the main function of the dynamometer. So over here, see, that is what I have written. Dynamometer is the device which is used to load the engine and measures the output torque of the engine. What is the formula that we use for output power of engine? Power is torque into angular velocity, tau into omega, which is same as tau into 2 pi n upon 60. So in your syllabus, there are mainly these 4 dynamometers. Out of these, sums are given on these first 2 dynamometers. These first 2 dynamometers are mechanical dynamometers. They are very easy. There is very less complication with these 2 dynamometers. So these are the traditionally used dynamometers. Nowadays, with the development of sensors and complicated electronics, we can also use eddy current dynamometer, and there is also a hydraulic dynamometer. But in sums, generally these first two are preferred and hydraulic dynamometer make up. So it is very important for us to know how exactly these dynamometers work, because only if we know how the dynamometers work, then only we will be able to solve the sums. Okay, so we will look at these dynamometers one by one. So the first dynamometer which we are going to see is a rope brake dynamometer. See, this is one of the simplest kind of dynamometers possible. Rope brake dynamometer works on the principle of absorption of the power by using friction. See, what do we do in this rope brake dynamometer? It is better explained in this diagram. See, in the rope brake dynamometer, this will be the device whose power has to be measured. In this case, it is an electric motor. But in our case, it will be what? It will be our engine. Out of the engine comes your crankshaft, right? Your crankshaft comes out of the engine. What we are going to do? We are going to add another long shaft onto the crankshaft. right? And then we are going to join the crankshaft and this shaft. We can join it using what? We can join it using a flange coupling, right? Or we can weld it. If it is a permanent setup, for example, our laboratory setup, we want it permanent. In that case, we can even weld it. But if it is a temporary setup which we have to remove and again put up, remove and again put up, then we can use a flange coupling to couple these two. So the device whose power has to be measured is coupled to a central shaft. On this central shaft, we mount a big pulley. Okay, so this is a big pulley that we mount on this central shaft. On this pulley, we put rotations of a thread, or rather rotations of a rope. Okay, so you can see this rope over here. There are several rotations of this rope. At the end of this rope, the rope will have two ends, right? This is the first. Then there are rotations on the pulley and the rope will come down. The upward end of the rope is connected to this spring reading. Okay, this is your spring meter which is used to measure the load, right? Spring balance, this is that. And bottom you see a stand. On this stand you can add weights. Okay, so basically weights like the ones that you see at your vegetable vendor, kind of those weights. They have like this horseshoe shaped weights. Okay, these are the kind of weights in this shape. So you can load it onto this, right? So by loading it onto this, you can increase the weight which is being applied. So basically what is happening, because of the weight which is added over here, because of that weight, there is a tension in this rope. There is a tension in this rope. See, this is your pulley. This is the rope which is wound around it. One is going up, one is going down. This is connected to a spring balance. Over here there is some weight. Because of that weight, there is some tension over here. Because of that tension, see, there is tension on this wire, on this rope. Between the rope and the pulley, there is some amount of friction, and because of that friction is providing the opposing force, right? This tension is leading to this friction, and this friction is providing the opposing force to the motion of the motor or the motion of the engine. So this is how a rope brake dynamometer works. Now if you want to do the mathematical analysis of this rope brake dynamometer, then see, how can we do the mathematical analysis that what is the actual amount of torque which is applied because of this rope brake dynamometer. Then see this. Okay, in this diagram, this is our pulley, right? And there is rope on that pulley which is going round and round, and this rope is over here. Now you will add some weight over here, right? You are going to add some weight on the lower pan. But what happens, even before you add some weight on the lower pan, there is some amount of weight of this rope, there is some amount of weight of this hook, there is some amount of weight of this pan. All this weight has to be subtracted from the total load that is applied. Okay, so that is why we use this spring balance. This spring balance measures the initial weight, the weight that we are not interested in, and afterwards we add whatever the weight we have to add onto that. So what is the actual load that is being acted on this pulley? The actual load that is acting on this pulley is weight minus spring reading. So W minus S. This is the actual load which is being applied onto the pulley. And this load is being applied at this particular distance, right? This load, I will just show you. See, over here, the load is being applied, and the load is being applied at this certain distance. What is the formula for torque? Formula for torque is what? R cross F. So if we know this radial distance, we know this F. What is this F? F is what? Weight minus spring reading. That is what this weight minus spring reading will be in kg. Okay, this weight minus, I will just show you the next slide. See, over here, this weight minus S, if it is in Newton, it is good, right? But if it is in kg, what we will have to do to convert mass into force? What we will have to do? Multiply this by acceleration due to gravity, right? So that will be our force. And what is the distance? Distance is this radial distance from the center of the pulley to this rope. This is the central distance. And what is this RE? This is the effective distance. This is the effective radius, right? What will it be equal to? See, you can clearly see over here. Imagine that this is your pulley. This is your pulley, and this is the rope which you have put on the pulley, right? This is the rope which you have put on the pulley. So what is the total diameter? The total diameter is diameter of the pulley plus 2 times diameter of the rope. That is the total diameter. What is the total diameter? Diameter of the pulley plus 2 times diameter of the rope. And if this is the total diameter, then what is the radius? Radius is total diameter divided by 2. Okay, so you got it. So this is basically how we can calculate what is the torque of the rope brake dynamometer. How are you going to calculate the torque applied by the rope brake dynamometer? First of all, what is the weight which is applied? Second, what is the spring reading? Then do W minus S. If W minus S is in kg, then multiplied by acceleration due to gravity, then you will get the load in newtons. If this is already in newtons, then you don't have to multiply it by acceleration due to gravity. After you get the load, you have to do what? Torque is what? Load into radial distance. So you need the radial distance. For radial distance, what do? You first take the total diameter. What is the total diameter? Diameter of pulley plus 2 times diameter of rope. And we want? We only want the radial distance. So this is the total diameter. Total diameter divided by 2 is the radial distance. So this is the torque formula for a rope brake dynamometer. Even if you do not remember anything else, please remember this formula. Okay, this formula, you have to remember this formula for a rope brake dynamometer. Torque is what? Force into radial distance. Force is what? W minus S. Remember, W minus S should be Newton. RE is what? Radial distance. And what is the formula for radial distance? D, which is D is diameter of pulley, plus 2D, where small d is diameter of rope, divided by 2. Sometimes what happens? Sometimes in sums they give the value of small d. In that case, you have to use this formula. Sometimes they do not give the value of small d. They say neglect the thickness of the rope. In that case, you can put this d as 0. So 2 into 0 becomes 0, and it is just d by 2. So that is how a rope brake dynamometer works, and that is how we measure the torque using a rope brake dynamometer, right? So given this, we will see a simple sum on this rope brake dynamometer. What is given in the sum? C. They are telling us to calculate the brake power of an engine. What is the formula for brake power? Brake power is torque into omega. What is omega? Omega is 2 pi n upon 60. Okay. So in this, what are the two things we need? We need the torque and we need the RPM. The RPM is directly given. See, 2000 RPM. So we need to find just the torque, which is known as the brake torque. We just have to find this torque and we can find the brake power. To find this torque, what is the formula that I just told you? What is the formula for a rope brake dynamometer? Force into radial distance. What is force? Force is W minus S. And what is the radial distance? RE, D plus 2D divided by 2. And you have to ensure that this W minus S is in what? Is in newtons, right? This is what you have to do to find the brake torque of your rope brake dynamometer. So what is the okay, see over here they have given applied load is 5 kg. So W is what? W is 5 kg. The spring balance reading is what? 200 gram. So 200 grams means what? 0.2. So this is given in kg. So see over here, applied load is 5 kg, spring balance is 0.2 kg. So what is the effective load? Effective load is W minus S. So 5 minus 0.2, that is how much? 4.8 kg. Now it is in kg, but we want it in what? Newton. To convert mass into force, we multiply it by acceleration due to gravity. So multiplying W minus S by G, we get what? 47.088 Newton. This is the braking force which is being applied. This force is being applied at this distance from the center, right? So what is this distance? This is d plus 2d divided by 2. So what is d? D is diameter of pulley. What is the diameter of drum? Pulley is also known as drum. Okay, this pulley is also known as drum. So what is the diameter of drum or pulley? It is 0.4 meter. And what is the diameter of rope? 5 centimeter, right? So substituting that values, 0.4 plus 2 times 0.05 divided by 2, we get actual diameter as, effective diameter as 0.25. Substituting it in this, tau is equal to R cross F. This is our force F, and this is our radial distance R. So we get our braking torque is equal to 11.772 Newton meter. And as I said, what is the brake power? Brake power formula is tau into 2 pi n upon 60. So substituting the value of tau and substituting the engine RPM, we get the brake power. So this is how rope brake dynamometer sums are to be solved. In exam, they will give you similar kind of thing. They will give you what is the applied load, they will give you the spring reading, and they will give you some diameters, and based on that you have to calculate the brake power of your engine. Okay, so this is how a rope brake dynamometer works. Now the second mechanical dynamometer which often comes in your sums is what? Is a Prony brake dynamometer. Okay, so see, the working of Prony brake dynamometer is even easier than rope brake dynamometer. What do we do in Prony brake dynamometer now? This thing, this is the shaft of the engine. Okay, this is the central shaft. Okay, see over here, what is this thing? This is this. Okay, this shaft and this connecting shaft which we are putting it, that is the one thing that I just shaded. Okay, I will show you. Remember this shaft, the shaft which is coming from your engine, that thing is over here. This is the central shaft. What do we do on this central shaft? We put a big flywheel, or we call this as drum. Okay, flywheel or drum. We put this big drum on this our central shaft, and around this central shaft we put two friction blocks. See, this is my one friction block and this is my another friction block. These friction blocks are also known as brake blocks. Okay, there are two friction blocks, one below, one above. The below friction block is fixed. This is fixed to this setup. Okay, and the above friction block, see, this is the torque arm. The above friction arm, this friction arm is fixed to this torque arm. Okay, these two things are fixed to each other, and this torque arm can be rotated, opened and closed. Okay, it can be opened and closed like your door. Okay, so how does this Prony brake dynamometer work? See, in case of Prony brake dynamometer, what do we have to do? We have to apply a braking torque. Even in rope brake dynamometer, what did we do? We applied a braking torque. What was the kind of force that we used to apply a braking torque? Frictional force, right? The rope is stationary. The drum is rotating. Hence, there is friction between the drum and the rope. That is how we absorb the power. In this case, what do we do? In this case, the flywheel is attached to the shaft. So as the shaft rotates, the flywheel will also rotate. And these brake blocks remain stationary. So there is friction between this flywheel and these brake blocks. And because of this friction between the flywheel and the brake blocks, the opposing force is applied. Okay, so this is how the Prony brake dynamometer works. Now, what is the torque applied by this Prony brake dynamometer? How will you measure the torque applied by the Prony brake dynamometer? Well, it is very easy. See, what is the torque? What is the formula for torque? Torque is force into radial distance, right? So in this Prony brake dynamometer, see what is the function of this torque arm? At the end of the torque arm, there is this hook. From this hook, there is again a pan. Okay, just like the pan that you saw in this. See, similar to this pan, there is a pan in your this thing also, Prony brake dynamometer also over here. On this pan, what we can do, we can attach the weights. What is the formula for torque? Torque is force into radial distance. So in this case, what is the force? Force is this weight applied, right? Force is this weight applied. Weight is a force. Mass into acceleration due to gravity is weight. Okay, so this is the force applied. And what do you multiply it by? Radial distance. What is the radial distance? Radial distance is the distance from the center of this drum to this weight. This is your radial distance, right? So weight into radial distance, length of the torque arm. So this is the amount of torque applied by the Prony brake dynamometer. So this Prony brake dynamometer absorbs the power developed by the engine in what form? It absorbs the power created by the engine in the form of friction. What is the friction between? The friction is between this drum, which is rotating with the shaft, and these brakes, okay, brake blocks. That is how Prony brake dynamometer works. Okay. So hopefully you have understood this. It is pretty simple. You will see an example on this, how Prony brake dynamometer works. See, what have they given us? They have told us to calculate the brake power of an engine where applied load is 2 kg. So this applied load over here, what is the applied load? It is 2 kg. Okay. The length of the torque arm from the center of flywheel is 1 meter. Length of torque arm from the center of flywheel means they have given us what length? From this center of arm to this. This is how much? 1 meter, right? And what they have told us to calculate what? Calculate the brake power of the engine if it is running at 2000 RPM, right? It is pretty easy. This is weight. This is in kg. We have to convert kg into what? We have to convert kg into Newton. So we multiply the weight with what? Multiply the mass with what? We multiply mass with acceleration due to gravity. So 2 into 9.81 is what? 19.62 Newton. That is the total force acting over here. 19.62 Newton, right? It is acting at what distance? It is acting at a distance of 1 meter, right? So what is torque? Torque is what? Force into radial distance. So what is the value of force? 19.62. What is the value of radial distance? 1 meter. So 19.62 into 1, which is what? 19.62 Newton meter. That is your braking torque. And what is brake power? Brake power is tau into 2 pi n upon 60, right? So substituting the value of tau is equal to 19.62 and substituting the value of n as 2000 RPM. We get brake power as 4109.2 watt, or it will be equal to 4.109 kilowatt. Okay, so this is how a Prony brake dynamometer works. So up until now we have seen two dynamometers. Both of these are mechanical dynamometers. First is the rope brake dynamometer and second is the Prony brake dynamometer. Both these dynamometers are doing what? Both these dynamometers are absorbing the power developed by the engine in the form of what? Friction, right? So after this we can see the next dynamometer. Okay, this next dynamometer is eddy current dynamometer. In the previous two dynamometers, what did we do? We absorb power using what? Using friction. In this case, we are not using friction. We are using the fact that a opposite EMF is generated. Okay. In this case, see, how does the eddy current dynamometer work? I will just explain in short. See, in eddy current dynamometer, what happens? Okay, I will show it over here. See, in this is the central shaft. right? This is the central shaft. Where is this central shaft coming from? This central shaft is coming from the engine. This engine is connected to this central shaft. Okay, these two are coupled. So as the engine crankshaft is rotating, this central shaft is also rotating. Onto that central shaft we put on a rotor. Okay, onto the central shaft we put on a rotor. Okay, this rotor is rotating inside this thing. Okay, this outer thing is known as your stator. Okay, inside is your rotor and outside is your stator, right? Whatever is rotating is known as rotor and whatever is stationary is known as stator. The stator is made up of permanent magnets. Okay, the stator is made up of electromagnets. Okay, the rotor is made up of a conducting material. The rotor is generally made up of a material like copper, and the stator is made up of temporary magnets, electromagnets. Okay, so what happens, what we do basically is we control the amount of current which is flowing to these electromagnets. Okay, see now what happens if the amount of current flowing to the electromagnets is zero. If there is no current, then what is going to happen? Those will not be magnetized. There will be no magnetic field. As there is no magnetic field, this copper central rotor will rotate easily. Okay, there will be no reverse force on this, right? To understand this better, I will just show you this one video. See, now this video, I have taken this video from YouTube only. See, in this video, what they are going to do, they are going to drop a magnet through a copper tube. Okay, and now see what happens when they drop that magnet. See, it takes so much amount of time to come down. Ideally, it should come down very quickly, right? But because what is happening inside, see, I will show it to you again. See, it is such a small copper tube. They are dropping the magnet and it takes so much amount of time for that magnet to fall completely down. Why is this happening? Because as the magnet is falling through this copper tube, see, as the magnet is falling through this copper tube, what is happening? As the magnet falls, a kind of a magnetic flux is generated inside this copper tube. Okay, and the magnetic flux generated inside the copper tube, it opposes the motion of the falling magnet. Again I will repeat. See, as this magnet is falling inside this copper tube, as that magnet is falling inside the copper tube, a reverse magnetic field is generated inside the copper tube, and that reverse magnetic field opposes the motion of the magnet. This same principle is being used in your eddy current dynamometer. In our that example, what was happening? A magnet was falling inside a copper tube. In our eddy current dynamometer, what happens? In our eddy current dynamometer, what is happening? The central shaft is made up of copper and the outer one is an electromagnet. When we supply power supply to that electromagnet, the electromagnet gets magnetized and it opposes the motion of this inner copper tube, copper shaft. Okay, this inner copper shaft motion is opposed by the electromagnet. More the electricity flowing into the electromagnet, more is the strength of the electromagnet. More is the strength of the electromagnet, more is the reverse magnetic field developed by the electromagnet, and more is the force applied on this central shaft. Thus, by controlling the current which is flowing through this outer electromagnets, we can control what is the force being applied onto this central shaft. And this is how we load the engine in eddy current dynamometer. Okay, but this is how we load it, and at the same time, but we have to measure what is the torque being applied, right? So to measure the torque which is being applied, what do? We put an arm out over here. Okay, this is an arm, and below this arm we apply a load cell. See, over here you can see this clearly. See, this is your eddy current dynamometer. Inside there is this shaft which is coming. The shaft is connected inside. Inside, what is happening? Inside there is that copper shaft. Outside there are these electromagnets. Okay, all these electromagnets are kept in what? They are kept in this stator housing. Okay, they are kept inside this stator housing. There are a large number of electromagnets, and out of this electromagnet stators there is an arm which comes out. Okay, this is the dynamometer arm, and this is the load cell. What is the function of the load cell? Whatever is the force acting on the load cell, that is measured by this load cell. That load cell is used to measure what is the force acting on it. Okay, this load cell deflects because of the force acting on it, and you can measure the force acting on it. Okay, so this is how your eddy current dynamometer works. Eddy current dynamometer basically opposes the motion of the rotor. And how does it oppose the motion of the rotor? It opposes it by using the magnetic flux which is produced, because the rotor is made up of copper and the outer housing are what? Electromagnets. Okay, and this is because of the eddy currents which develop inside this copper. Okay, and but this development of eddy current this development of eddy current also leads to generation of a lot of heat. That heat has to be removed. Hence, to remove all that heat, we also have coolant flow. See, from here the coolant flows into the dynamometer, and from here the coolant flows out of the dynamometer. So this is used to cool down the eddy current dynamometer. So this is how an eddy current dynamometer works. It is possible that in the exam they might ask you to write a short note on eddy current dynamometer. So what do you have to do? You have to draw this diagram. You have to explain that this rotor is made up of copper. This outer stator is made up of an electromagnet. We can control the amount of current going to the electromagnet. By controlling the amount of current going to the electromagnet, we can control what is the magnetic flux which is developed, which opposes the motion of this shaft. And there is a dynamometer arm over here which is connected to a load cell, and here we can measure what is the load being applied onto the eddy current dynamometer. If we know the load, and if we know the length of the dynamometer arm, this is load. Load into acceleration due to gravity is force. Force into the length of the dynamometer arm. This will be your braking torque. Okay, so this will be your braking torque. So this is how an eddy current dynamometer works. And the last dynamometer in your syllabus is hydraulic dynamometer. See, basically how a hydraulic dynamometer works. In a hydraulic dynamometer, there is an outer casing. This is your outer casing, right? This outer casing has, if you have seen impellers, see, impeller is what? Impeller are the, see, when you have to generate electric power, right? This is your rotor. On this, there are this shaped, moon shaped kind of things, right? So water falls on this, and this water falls on this, and because of this, this rotates, right? So this moon shaped thing, these are your impellers. Okay, so in a hydraulic dynamometer, how it works? There is an outer casing. Outer casing has these impellers. Okay, this outer casing is round. This is your side view. This is your front view. It has these large number of impellers over here. Okay, the outer casing also has impellers, and inside there is a rotor. This rotor also has impellers, right? This rotor also has impellers. Both the rotor and the stator have impellers. And what happens? There is a pipe for intake water, and that water, see what is happening. See, this is your inner housing. This is your inner part. This is your outer casing. See, over here you have an impeller. Over here also you have an impeller. Water is coming into this. Between these two impellers, water is coming. So what is this impeller doing? This impeller is forcing water in this direction, right? What is going to happen? Water is going to be forced onto this impeller. See over here, I will just draw it again. This is inner, this is outer. We will focus over here. This is one impeller, this is another impeller. The casing is fixed. Okay, the casing is fixed. It is fixed to the ground. And the inner part, it is connected to your shaft. It is connected to an engine crankshaft. So the inner part is going to rotate. The inner part is going to rotate. The inner rotor is going to rotate. The outer stator is fixed. As the rotor rotates, there is water flowing between the rotor and stator. Okay, there is water flowing between the rotor and stator. So as the water is flowing between the rotor and stator, this impeller of the rotor, it is what? It is pushing the water outwards. This water which is pushed outwards hits this impeller. This impeller is stationary, right? So whenever water is going to go and hit this impeller, there will be some amount of force which will be acting on this impeller, right? Some amount of force will be acting on this impeller because of this water hitting it. That force can be measured using your load cell. That force can be measured using your load cell. See, this works, hydraulic dynamometer works similar to your uh, uh, eddy current dynamometer. Hydraulic dynamometer works similar to your eddy current dynamometer. In eddy current dynamometer, what is happening? The copper shaft is rotating and the magnetic flux is trying to stop that copper rotor from rotating. What is happening in hydraulic dynamometer? In hydraulic dynamometer, there is this central rotor. On this central rotor, there are these impellers. The water is flowing onto these impellers and these impellers force the water outwards. Then this outgoing water hits the impellers of the stator. The stator is stationary. So when water hits the stator impellers, there is a force acting on the stator impellers. This force is transferred to the stator and this force is then transferred onto the load cell or torque meter. Okay. So here also, if we know the load which is acting on the hydraulic dynamometer and if we know the distance between the center to this point, then we can calculate what is the torque. Torque will be force into radial distance. Okay, so this is how the different dynamometers work. Okay, so there are basically these four dynamometers. In the first two, rope brake and prony brake, what are we going to see? It is in name itself, brake. We are trying to stop it, right? Using what? Using friction, right? In the third kind, in our eddy current dynamometer, the central copper shaft is being stopped because of the magnetic flux produced by the electromagnets. And in the third one, our hydraulic dynamometer, what is happening? The rotor is rotating, the rotor forces the water outwards, that water hits the impeller shaft, impellers on the stator, and the force is transferred to the stator. This is how hydraulic dynamometer works. So these are basically the four dynamometers which are in your syllabus. It is possible that they might ask you to write a short note on any one dynamometer. Okay. So what I will suggest is you do these first two dynamometers, rope brake and prony brake dynamometers well. Draw their diagram, understand this formula, how the force comes, how the radial distance comes, and that should be all. Okay. Thank you.